There's another thing here that might be quite interesting for you guys. When does a circle appear as a circle? Which I always, I don't know if you've heard the Glober argument that if you're looking at a clock on the wall, right, and you go to one side of the clock, then the clock will appear to be an ellipse. And Globers will always say it can't work in a flat plane. You know, if the sun is a circle and it's going round, then it should change its shape, right?
Right.
Yeah.
And, you know, intuitively, yeah, they're kind of correct, right? You know, you can look at a circle on a wall, and if I move to the side of it, then it will look elliptical. But there's actually a few things that, again, very subtle in there. And I found an old English translation of Euclid's Optics. So Euclid did not only just do the elements of geometry, Euclidean plane geometry, he also wrote a pamphlet about optics. And the very first English translation ever made was in 1950. You got to believe that, right? I mean, it's amazing, right? And in this translation of Euclid Optics into English, he's got some theorems in there that describe how a circle appears. So I went through this paper. This is the original proof from Euclid, right? In blue. And I then basically remodeled them in GeoGebra. So let me just go down to it here. And basically what he's saying is that if you've got a circle here, I'm just drawing the circle now on the ground, and I'm directly above the circle, directly above the center of the circle, sorry, at any altitude, then when I look down at that circle, it always is going to appear to be a circle. It'll get smaller, but the higher I go, or the lower I come down, it's always going to be a circle. The reason for that is that the angle subtended at this point, the angle subtended at the eye, if that's where my eye is always going to be equidistant to any of these two side points or any of these 2 points. So any diameter will appear to be the same ratio. And if two diameters are the same, then it must be a circle. If two diameters are not the same, then it's an ellipse, right? So that one is very clear, that if I am straight over the center of a circle, or I'm facing, maybe a circle's drawn in a wall and my eye is directly opposite the center, then I can move back or move forward. It's always going to look like a circle to me. Agreed?
Agreed.
Yep.
But there's also another one where everything will look as a circle to me. Again, this is the Euclidean original proof, right? And I modeled it in GeoGebra again. And basically, it's the special case where this radius of the circle, so this from E to B, the distance you are away is the same as the radius. So in the first one, it didn't matter how far I went away from the circle, it would always appear as a circle, just get smaller or bigger. And in this case, it's that I am exactly at that position away from the circle that is also the radius of the circle. It's a special case, right? And if that's the case, then basically using Thales' theorem, you know that that is always going to be a 90-degree angle. It doesn't matter where you are. And basically what it means is that if you are anywhere on a sphere that is the same radius as the circle you're looking at, so the circle I'm looking at is this green one, the eye is on the surface of a sphere. It doesn't matter where I go in this sphere, this thing is always going to appear as a circle to me.
Wow, yeah.
So why does the sun always appear to be a circle?
Because of the...
Again, we're back to the spherical geometry and the way the eye works.
Geometry of the eye. Wow. Yeah, because with our limit of how far we can see and everything like that, it's not like we're seeing it, you know, shrink away and go off into the distance. There has to be special circumstances. You have to be high up on a mountain where you're elevated and not so close to the ground. So this makes so much sense. So it's always pretty much about the same distance away from us.
Yep.
The way we're seeing it.
The way we're seeing it is basically all the same way. And if we agree that the circle diameter of the sun, if this is the sun I'm looking at, right? The green one, and it's 32 miles, then it means that it's 16 miles is the radius basically of the sphere. And if I'm anywhere on that sphere, then that will always appear to be a circle, because the distance from here to here, or the distance from there to there, is always going to be the same. And the way that you know something is a circle is if two diameters are of equal proportion in a one-to-one relationship. A condition where a circle always appears as a circle. And that's when the enclosing angles are the same. And basically this is Euclid again. I've just modernized it, so it's not coming from me, but what this guy was saying, that the enclosing angles, as long as they're the same, then it also looks like a circle. So here it is. If that's where my eye is, and I'm looking at this circle on the ground, but you could just transpose the whole thing, right? I could be on the ground and the circle could be in the sky. Mm-hmm. So, you know, geometrically, it doesn't matter. Then this thing will look like a circle when the enclosing angles next to each other are equal. So it doesn't have to be directly above. That was case number one. It doesn't have to be on a sphere. That was case number two. There is also the case, the special case, where when the enclosing angles are the same, it will also look like a circle as well. So I was just trying to find out, what the hell does that mean? You know, why is it that we see a circle as a circle?